we present InteractVLM, a novel method that estimates contact points on both 3D human bodies and objects from a single in-the-wild image, visualized here as red patches. These inferred contact points enable joint reconstruction of humans and objects, which is critical for applications such as assistive robotics and mixed reality. There are methods that estimate 3D human bodies and methods that estimate 3D objects, but few that put these together. Existing methods rely on expensive data capture systems, which do not scale or capture data in lab settings, which does not reflect the complexity of in-the-wild scenarios. Knowing the contact points on humans and objects could significantly improve joint 3D reconstruction from an image. However, there is a lack of in-the-wild training images paired with ground truth contact labels for both 3D humans and objects. The problem becomes even more challenging when humans interact with multiple objects. In this case, current methods treat contact prediction only as a binary classification task, so they only detect whether a body part is in contact with any object. This fails to capture the rich semantic relationships of multi-object interactions. To address this gap, we introduce a novel Semantic Human Contact estimation task. This involves predicting the contact points on bodies related to a particular object given a single in-the-wild image. To reason about the rich semantic relationship of multi-object interactions and to avoid data scarcity, we propose a new paradigm for scaling and reasoning in the wild. Specifically, we exploit the broad visual knowledge of large vision language models, or VLMs, by fine-tuning these models on small 3D contact datasets. We call this method InteractVLM. At the heart of InteractVLM lies a reasoning module based on a VLM. Given a color image, this module can be asked to produce reasoning tokens that facilitate 3D contact localization. A naive way to exploit these tokens is to employ a foundational localization model that takes these tokens as guidance and highlights the 3D contacts. However, such existing foundation models operate in 2D while contact is 3D. To use 2D foundation models for the task for 3D contact localization, we develop a novel Render-Localize-Lift framework, or RLL for short. In RLL, we take three main steps. First, we render the 3D shape of a canonical simple H body and a 3D object as 2D images from multiple viewpoints. Second, we pass the rendered images into a localization model to predict 2D contact masks for both the body and the object. Third, we lift the predicted 2D contact points to 3D points, namely we revert the projection of the first step. Even though we recast our problem to 2D, the localization model is not 3D aware. This means that contact detections in one view do not necessarily agree with ones in adjacent overlapping views. To tackle this, we build a novel multi-view localization model called MV-Loc. MV-Loc takes two main steps. First, it transforms the reasoning token, provided by the VLM, to 3D. Second, it enforces a 3D loss on the contacts lifted from 2D contact masks. We quantitatively evaluate our method for in-the-wild 3D contact prediction on bodies and on objects, using the Damon and Payad datasets, respectively. For bodies, we evaluate both for the traditional binary contact estimation and for our new task of semantic contact estimation. For all tasks, we find that InteractVLM outperforms the prior work. For more details, please refer to the main paper. Here are the qualitative results for the task of semantic human contact prediction. We compare our method InteractVLM with Semantic Deco. In the third row, see how Semantic Deco predicts the entire body as contact for the bench category. Here are the qualitative results for object affordance prediction. We compare our InteractVLM with state-of-the-art method for object affordance. For the mug case, see how our method accurately predicts affordance. For more results, please refer to the supplementary paper. Finally, we demonstrate that contact estimated by InteractVLM can be useful for improving the accuracy of 3D joint human object reconstruction from an in-the-wild image. To this end, we develop an optimization-based method to fit a body mesh and an object mesh to an image using InteractVLM's inferred contacts. Here are some qualitative results. Here we compare InteractVLM with FOSA, the state-of-the-art method for in-the-wild joint human reconstruction. Unlike FOSA's handcrafted contacts for bodies and objects, our reconstruction is guided by InteractVLM's inferred contacts. For the task of binary human contact, we compare the F1 score of several InteractVLM model versions, trained with a varying size of 3D training data. Even with significantly less training data, our method outperforms DECO, which is trained on 100% of the data. To conclude, we present InteractVLM, a novel model that infers 3D contact points on both humans and objects. Importantly, by leveraging the broad visual knowledge of vision language models, InteractVLM minimizes the reliance on expensive 3D contact annotations. We show the usefulness of contacts inferred by InteractVLM for both the body and object, for estimating 3D human-object interactions. This is done for the first time for single in-the-wild images using inferred contacts. The code and models are available for research. Thank you for watching.